Alright, number one, we need to get the end behavior. So we first need to put this in standard form, and it is. It's the largest exponent down to the smallest. So it's an odd function since it's to the third power, and the lead coefficient is a negative. That tells us that from left to right it goes downhill. It doesn't make a difference what happens in between. I know I keep saying that, but it's important. It doesn't matter what happens in between here. The idea is that it goes downhill, meaning it goes from an up, down. So because it's an odd function, it has split ends. So we're going to have the limit as x approaches negative infinity is positive infinity, because as I'm going left, it's going up. And the limit as x approaches positive infinity is going to be negative infinity since it goes down. And that's your answer. This one over here, again, it's a cubic function, so it's odd. Lead coefficient is negative. And it's in order. So it's the same exact thing as number one. So let's just write that out. The limit as x approaches negative infinity is positive infinity, and the limit as x approaches positive infinity is negative infinity. Because again, just like the other one, if it's odd, it has split ends, and if it's negative, it goes from up to down. Doesn't matter what happens here. Alright, so we want three things here: end behavior, turning points, and intervals. So the end behavior, we're going to look at this first, the equation. It's an odd function and it's positive for the lead coefficient. So that means, whatever happens kind of looks like this. It goes uphill from left to right. So for the end behavior, we're going to say that the limit as x approaches negative infinity is negative infinity, because as I go left, it goes down. And the limit as x approaches positive infinity is positive infinity, because as I go right, it goes up. That's the end behavior. To see if there's any turning points, let's turn the calculator on, clear anything out that might be there. So 3x cubed. 3x raised to the third. And then let's look at the graph. We can zoom in the origin here just to see if there is any turning point. Let's put a box around that. And as you can see, it kind of just flattens out here and then goes up. It never gets to a point where it goes down, then up. You're constantly going up. So there's no turning point. For the increasing, decreasing intervals, it's constantly increasing. So for the increasing interval, you would say from negative infinity to positive infinity. It's constantly increasing. So that one's a simple one. This one over here, it's in standard form, it's odd, and it has a negative leading coefficient. That means from left to right it goes downhill. So the limit as x approaches negative infinity is positive infinity. The limit as x approaches positive infinity is negative infinity. So that's the end behavior. For the turning point, we're going to get the calculator out again. So we have negative 9x to the third minus 2x squared plus 5x plus 3. Let's take a look at the graph. Alright, so let's fix the window a little bit here. And then take another look at the graph, see if it's better. Yep. So there is definitely turning points here. So let's zoom in over there. So we clearly see the local min and the local max. So let's do second trace minimum. Move to the left part of it, then to the right. So negative 0.51. So negative 0.51, comma 1.12. Let's write that down. So for the turning points, negative 0.51, comma 1.12. Now let's do second trace 4. Let's move to the left of it, then to the right, and then guess. And then we're going to have 0.36, comma 4.12. So 0.36, comma 4.12. It would probably serve us well if we just looked at what the graph would look like here. Something like this. Where this is your first point here, and that's your second point there. And let's just really quick put down where it's negative, it's going down, then here's positive, and then down again. So for the increasing interval, we're going to have from the x-coordinate here to the x-coordinate there. So negative 0.51 to 0.36. For the decreasing intervals, we're going to have negative infinity to this x value, and from this x value to positive infinity, 0.36 to positive infinity, and that's it. Alright, so we're going to determine the degree now, so we have to check and see if the x values go up by 1 or by 2 or by 3. This goes up by 1, it's evenly spaced, so that's good. So we've got a bunch of terms here. So let's subtract. Negative 3 minus negative 9 is 6. Negative 9 minus negative 9 is 0. Negative 9 minus negative 9 is 0. Negative 9 minus negative 15 is 6. So the first doesn't work. 6 minus 0 is 6. 0 minus 0 is 0. 0 minus 6 is negative 6. It's not a second degree polynomial either. 6 minus 0 is 6. 0 minus negative 6 is 6. So it's a third degree polynomial because it came out to be the same number. Alright, here's another box problem. So if you can draw the box, then everything is in terms of width. So the length is 2 less than the width, so w minus 2, your width is w, and the height is 4 less than the width, so w minus 4. So the volume is going to equal w times w minus 2 times w minus 4. So if we do that out, we're going to have w squared minus 2w times w minus 4. That's what that multiplied gives you this. And then we FOIL this out, we'll get w cubed minus 6w plus w squared plus 8w. So let's write that down as our equation. W cubed minus 6w squared plus 8w. Now to graph the equation, let's get the calculator out. So we'll have x to the third minus 6x squared plus 8x. Let's just get an idea of what it looks like, and I'm going to fix my window now. Alright, so let's plot some points. 0, 0, 1, 3. 2, 0, 3, negative 3. 4, 0, 5, 15. So 5, 15 is going to be way up here. So we kind of know now that it goes up to there, down to there, and then back up. So let's try to do that. Alright, so here's where it increases, then decreases, then increases again. So the part C where it increases, we're going to have 2 intervals, and where it decreases, I'm going to have 1 interval. So I need to find my turning points. So second trace max, I'm going to go to the left of that point, and to the right of it, and then enter. So that's going to be 0.85, let's say, comma 3.08. And let's just write that down. So the local max, 0.85, comma 3.08. And then let's find the local min. Second trace 3. To the left, to the right, 3.15, comma negative 3.08. So 3.15, comma negative 3.08. Okay, so where it increases is going to be from negative infinity to the x value here, which was 0.85. And from this x value, which was 3.15, to positive infinity. Where it decreases is from that x value to that x value. So from 0.85 to 3.15. And you're done. Alright, we want to solve the system, so what we're going to do is we're going to set them equal to one another. If I subtract x squared from both sides, they cancel. So I'm going to subtract x. So I'm going to have x equals negative 20. That's my only x value. So we're not done yet. Remember, we're solving the system of equations. That means we're getting a coordinate. So there's my x coordinate. I need to find out what my y coordinate is now. So if I plug in negative 20 for x, I'm going to have y equals 400 minus 40, which is 360. And that's your coordinate. What's the discriminant? Remember, it's b squared minus 4ac, so b is -1, so -1 squared minus 4 times a times c. So we're going to have 1 minus 4 times 4 times 5 is 80. So -79 is your discriminant. That just tells you that you're going to have imaginary solutions, meaning you're not going to have any real solutions. Simplify 2 divided by 5 minus I. What we're going to do is we're going to multiply the top and bottom by the conjugate of the bottom. So 2 times 5 plus I is going to be 10 plus 2I. Down here we'll just do F and L of FOIL, so 25. And the reason why we do that is because they're conjugates. Negative I times positive I is negative I squared, which is negative, or the opposite of -1, which is positive 1. So 10 plus 2I over 26. Now all three terms can be divided by 2. So to simplify, we can do that. So 5 plus I all over 13. And last, explain what it means to rationalize a denominator. You rationalize a denominator when you have a denominator, for example, 2 over 1 plus root 3, or you have a denominator like 3 divided by 2 plus I. If you have a denominator that has either an imaginary value or an irrational value, then you multiply the top and bottom by the conjugate. And what happens is the irrational part of the denominator becomes rational after you multiply by the conjugate. So when you rationalize a denominator, you're taking a denominator that once was irrational and you're making it rational by multiplying the top and bottom by the conjugate.